Sì, sì, tutto ok.
Ok.
Yes, professor.
Okay. And you can hear you can see the whiteboard, right? Yes. Yes, tell me yes. Yes.
Sì.
Okay.
Yes, professor.
Okay. You can't imagine the shock when your recording hasn't worked, so you have to do it again. It's not very nice. So that's why I keep on asking everyone. Okay, so finally, we have now concluded the thermostatics part 1 of the course, the thermodynamics or thermostatics part of the course, okay? So now we are essentially doing this. We're moving from thermostatics to what we call chemical kinetics. Okay? This is a pretty big jump that we're doing, okay? Because in thermostatics, if you remember, we said that there is no time as an independent variable, no time t measured in seconds. And in fact, there is even no space, okay? X, okay, in meters, okay? So it's a homogeneous, okay, pieces of matter, okay, with no special direction. And really, the evolution of any phenomena is so-called quasi-static, okay? So it occurs, let's say, you should picture it as occurring in infinite time, okay? Now, chemical kinetics really is the realm, okay, of real processes, okay? So these were quasi-static. These are real processes. Okay, by real process, we mean processes that really move away or substantially away from equilibrium, okay? And can, for example, have an initial and a final state, an initial metastable state, for example, it could be, and a final equilibrium state, okay, or thermodynamic state. But what happens in between, we're going to monitor through an evolution in time. So we're actually introducing now time. Introducing time. T measured in seconds. So for the first time now, we're really introducing, let's say, independent variable, time, and therefore the evolution in time will essentially be monitored or studied through ordinary differential equations, okay? Differential equations that will introduce derivatives in time, okay? So it's a pretty big jump in this respect, okay? We're moving from a theory that does not have, that is a concentrated parameter theory in a way, in which we're studying states of equilibrium, which can be spontaneous states or they could be constrained states. On the other hand, here we're really moving away from these states, okay? We're really outside of that realm. We can be very far from equilibrium states. And we're really trying to study real processes which are, for example, collision processes between molecules. We want to understand how fast, okay, the overall process evolves in physical time, okay? So this time here is physical time. So I will give you, for example, two examples, okay? The production of rust on a metal, for example, iron oxide on a metal is a very, very slow process, right? By saying slow, I am intuitively introducing a time scale. And that's what I really want to study, that sort of time scale. On the other hand, we know that if you have a combustible mixture of methane and air, okay, this will react very fast, okay, and it's a very rapid reaction. So the time scale will be very short. So the question behind chemical kinetics is really how fast, okay, is this is this chemically reactive process, okay? So how do we study this? So we forget now about where is it? About the old stuff now. Sorry. Okay, and we concentrate on chemical kinetics. Okay. The first concept that we should introduce is the concept of rate. Okay, rate or velocity. Okay, of the chemical process. And again, if the rate is very high, then the time scale is very, very small, very short. The evolution is very fast. We'll see that most of the combustion processes are very fast for a very specific reason. So how do we define this? And this is what we're going to do right now. How do we define a rate or velocity of the reactive process, so-called rate of reaction? Okay. Well, we know that species, the relative quantity of species is measured in molar concentration, right? Now we're going to be using either, for species I, we're going to be using either this notation here, CI, but more frequently we're going to use this one, which is more common in sort of chemical engineering. The species MI between brackets, the square brackets, this essentially means, okay, the molar concentration of the species MI, okay? So it's essentially the number of moles of I divided by the volume. So it's measured in moles per, I don't know, centimeter cubed. Okay? So, so if we consider the molar concentration as the relative, abundance of species I in a mixture, for example, it is totally reasonable that we introduce a reaction rate which we can call, for example, omega, okay, which has units of rate of change of molar concentration, okay? So essentially, moles per centimeter cubed, okay, divided by seconds, okay? So it's a rate of change of molar concentration, okay? It is a little bit more complicated than this, as we will see, because consider like a generic global reaction, okay, of which we would like to understand the rate, okay, the rate of reaction. So a global reaction, for example, can be expressed as A moles of A plus B moles of B, etc., okay, which give, for example, here we're only preliminarily considering only an irreversible reaction, okay? Giving some products P, Q, etc. Okay, this is relevant, really, what we're having. Okay, here. Well, first of all, we know what to write for this process. Okay, for example, we know the definition of the progress variable. Okay, in terms of the infinitesimal increment of the reaction progress variable, which is given by, well, if we're talking about reactants here, so we have the classical minus sign, okay, times the variation of the number of moles of A, okay, and so on, okay, well, minus 1 over B, the infinitesimal variation of B, etc. And then clearly this corresponds to plus 1 over P, the increment of number of moles of P and Q. Sorry, this is an equal. D and Q, etc. Okay? So think about it. We have a number of moles here. So for example, if we divide by the quantity volume times dt, okay, we have essentially something that is measured in moles per centimeter cubed, because we're dividing by a volume and the number of moles by a volume, so we have a molar concentration, and by dt, so we're dividing by a time. So essentially, we can define a finite reaction rate omega as this quantity here, 1 minus a dna by dt, okay? Where, sorry, oh, what I meant to say was d and dA by dt. So clearly, by dividing by the volume, we're introducing the molar concentration, okay, here. And the same thing for B, okay, etc. Well, I'll write it for the full. So essentially, the only thing that we have to be careful is that now moles divided by volume become molar concentrations, okay? That's all. And in fact, this is generically d1 over the volume, okay, times the rate of change of the progress variable, okay? So this is the reaction rate. As you can see, it's a unique quantity, okay? So it is associated not to a single species, but actually to the reaction. That's why it's called rate of reaction, okay? And the only difference between the rate of reaction and the actual rate of change of the molar concentrations, okay, is the fact that we are weighing, essentially, the rate of change of concentration by the respective stoichiometric coefficient. And we're doing this for a very simple reason. I'll simplify things for you. For example, suppose we have this reaction, 2B giving Q, okay? So through this definition here, the rate of reaction would be minus a half, okay, the rate of change of concentration of B, okay, and it's also plus 1 over 1, the rate of concentration, molar concentration of Q. Clearly, the signs, you have to be careful here. Clearly, in an experiment, if you evolve this reaction, the rate of change of the molar concentration of B will be negative, because as you can see in an irreversible reaction like this, B will be depleted. So dB by dt will be decreasing, so it will be negative, and this will be positive. So clearly, negative times negative is positive, and the fact that there is a 2 here clearly shows you, essentially, that the rate of depletion of B, okay, let's call it with a minus sign, okay, is really 2 omega, whereas the rate of depletion of Q, sorry, the rate of increase of Q is equal to omega, okay? So the rate of depletion of B is twice, okay, the rate of production of Q, okay? And therefore, what we do is we always weigh, okay, the rate of depletion of each species by its stoichiometric coefficient, okay? In this case, 2, as you can see here, okay? So we can now generalize this rather simple concept to a generic reaction, okay? So the reaction is always in the form nu prime I mi, okay, and need double prime nu double prime mi, okay. So how do we define the reaction rate in exactly the same thing? We remind ourselves that dni over the difference in stoichiometric coefficients, okay, this is for all species, is equal to d xi, right? So we can divide, for example, by dt, okay, and we have the rate of change of progress variable, okay, and then by dividing by the volume, okay, we have essentially that 1 over the stoichiometric coefficients, okay, will give times, now I'm dividing by volume, so this becomes now the molar concentration by dt, okay, which is equal to 1 over v. And that will be equal to the rate of change, okay? Usually in the notation that we're going to be using, okay, we're going to use omega without any subscript, okay, for the reaction rate, whereas we're going to use the notation omega I, okay, for the rate of change of the molar concentration of the species I, okay? And the only way in which these are the same, okay, is when essentially ni double prime minus ni prime is exactly equal to 1, okay? So if this factor is equal to 1, then omega I is actually equal to omega, okay? But that's not too exciting. Although this case here is rather common when you have that quantity equal to 1, okay? Let's take a closer look at now some examples, okay? For example, let's take the thermal decomposition of nitrogen pentoxide. So we have this molecule here, okay, which under certain conditions decomposes, okay? It breaks down into nitrogen dioxide, okay, and oxygen, okay? So again, let's only look at the irreversible, for the time being, let's look at the irreversible reactions, okay? Now, again, remember, we have abandoned the concept of equilibrium. Now, really, we're interested in the temporal evolution, okay? How fast does nitrogen pentoxide, in fact, I said pentoxide, I wrote dioxide, this is a 5. How fast does it deplete, okay? How fast does it its molar concentration decrease. Okay. Now, first of all, we gave a definition. Okay. So let me just remind you that this is what we call rate of reaction. So it's a definition. Okay. And as by definition, the rate of change of each molar composition weighed, molar concentration weighed by its stoichiometric coefficients. Okay. I'm just repeating this so that we get the hang of it. Right, this we know. Now, that is really not an exciting prospect because this is just a definition, okay? So that's what I call reaction rate. But what if I'm interested in actually an expression for the reaction rate, which is not clearly this, but it's, for example, an experimental correlation which can relate the reaction rate to some observable, okay? For example, look at this function here, this reaction here. I can, in the laboratory, I can monitor, for example, the function O2 of T. So I can monitor the instant by instant the molar concentration of oxygen. Okay. So this is the instantaneous correlation of oxygen. Okay. So I can do it experimentally. This is produced by the, as you can see, by the decomposition of a pentoxide. So that's what I expect to observe, some increase, okay, in time of the molar concentration of O2, okay? And this is, again, experimental. Okay, I haven't done anything other than monitoring, okay, by measuring, I don't know, the volume occupied. This doesn't really matter now, the technique, okay? Now, we know also that the rate of change, sorry, the rate of reaction, omega, is exactly equal, okay, to the time derivative, okay, to the time derivative of this. And in fact, the time derivative of oxygen. And in fact, the time derivative of oxygen is minus a half the time derivative of nitrogen pentoxide. So I could even, by measuring O2 experimentally, I can even derive the rate of change of nitrogen pentoxide because it's minus twice the increase of O2. So I take this function here and I multiply it by -2, something like this, okay? And this would be N2O5, okay? So now I've done an experimental campaign, okay? And I almost know everything, okay? I know the function O2 as a function of time. I know N2O5 as a function of time, etc. Okay? And I know that omega, okay, is the rate of change. So it's the slope. So for every time, at every time t, I can calculate the slope. Well, suppose this is the slope, okay? Okay, and from this, I can compute omega, okay? Now, this is where I build my theory, my sort of chemical kinetic theory, okay? Because what I can do here is the following, for example. I can imagine of trying to correlate, okay, omega that I calculate from the slope of this curve to some instantaneous value, for example, of concentration, okay, of nitrogen pentoxide, okay? And surprisingly, okay, starting from an initial t equals 0, I'll be over here. So omega will be this slope here, okay? This is N2O5, the initial, okay? Surprisingly, okay, if I monitor the rate of reaction, okay, I have, now of course, I mean, you can imagine how this is supposed to go through here. So, okay, let me try again, okay? But I'll draw the line first, okay? This is a line, because you could draw a line, okay? And if I monitor, if I take my experimental points, surprisingly, okay, I find a perfectly linear relationship, okay? So experimentally, I find that this omega is actually some constant, okay, some slope times the molar concentration of the nitrogen pentoxide, okay? That is remarkable because it's very simple. It's a very simple kind of relation, okay? Whereas this was a definition, okay? This is actually a relationship, and I've done a relationship that comes from experiments. So this is like, you can write this definition. You can write this over here. This is a definition, okay? And this is an experimental correlation, okay? How important this is, well, now I won't go into too much detail here. I will suppose that you keep the temperature constant, so this becomes a constant. In fact, this is not generally a constant, it's a function of temperature. And this is the instantaneous molar concentration. Clearly, we start from T equals 0. This would be clearly the initial concentration at 0. And this is T equals sort of final. Okay, when we deplete completely here, TF. Okay, when we deplete completely the reactant. Okay. Why is it important? Well, you join now, or not join, but put together the definition of omega, which, for example, is minus a half the rate of change of the molar concentration of N2O5. This can now be placed equal to this. Okay, this is my definition, and this is my model, my experimental correlation. Okay, the surprising fact is that now my model allows me to really derive an expression for every time, every instant. I can derive analytically, okay, for every initial condition, for example, by solving this this equation. So it will scale. Now forget the initial conditions. Now it will scale like e to the minus 2 kt. Okay, and so we are actually able, through this model, to actually derive for every condition, for every condition, it's not totally correct because this K here, let's say for the same temperature, okay? Derive an analytical expression for the depletion instant by instant of my reactant, okay? Which is not too bad, okay? Now, it is quite remarkable. It's not always that easy though, okay? I'll give you another example, which is a little bit more complex. Now, remember here, I'll anticipate this. This is a linear kind of relationship. And try to remember that there is a 2 here, okay? Now, I'll give you another example, okay? This additional irreversible reaction, nitrogen monoxide plus Cl2, okay? Doesn't really matter what these are, but okay? Now we have the reaction of 2 molecules to give this molecule here. I can do exactly the same, okay? I can carry out at constant temperature this in the laboratory, okay? I can monitor, for example, the rate of production of this molecule here, okay? And come up with instant by instant with an expression for omega. Now, what I'm trying to do, the rate of reaction, is to do something similar to this, okay? Is there some kind of correlation between omega and the instantaneous molar concentration of my reactants? Well, there is, okay? Experimentally, we find that omega is equal to K, okay? Another sort of constant. And then what we have now 2 reactants, okay? So what I find is this correlates to the product of the molar concentrations of the 2 reactants. It doesn't end here because NO, okay, is actually to the power of 2. So what I do essentially in order to decrease the confusion here, before it was pretty simple, right? We were correlating it to just a simple unique molar concentration of one species. Now what I'm doing is I find that this linear correlation happens between essentially this group, okay? So if I do my experiment and I calculate these quantities, I take and then I calculate this group here, okay? This correlates linearly with omega, okay? So, which is a little bit more complex, first of all, because I have 2 reactants. So one would expect, okay, so maybe it's the product of the concentration of the 2 reactants. In fact, it's a little bit more complicated because you see, one of the reactant is at the power of its stoichiometric coefficient. In fact, I said if you could remember this 2 here, you see now the exponent here is only 1 for some reason, okay? So there is a logic, but we haven't really understood what the logic is yet. But we can say that they're fairly simple correlations of these. Now, clearly, these are nonlinear correlations, okay, with respect to the single individual molar concentrations. But it is linear with respect to this whole group here, okay? So in general, Okay, my theory could be sort of generalized by saying, okay, given the generic process that we saw before, A plus B, okay, etc., giving some products, okay, the rate of reaction can be expressed, okay, as some sort of rate constant nothing. I just cannot, I'm not able to write with this. It's something that I will have to face. Rate constant. And then the product of each molar concentration, okay, I can go on and on. If this is a global process, I could have more than one reactant, for example, each to some power, okay? I'm not specifying now what power it is, but it's some power, okay? Which I call, for example, alpha, beta, and so on, so on. This is the rate constant. These powers, okay, have a name, and they are reaction orders. So that means that, for example, species A, okay, appears with reaction order alpha, or the reaction is order alpha with respect to A, order beta with respect to B, okay? And these alpha and beta, generally speaking, are experimental. So K, alpha, and beta generally are experimental results. Okay? I will have to find this group that correlates linearly with omega. Okay? Bear in mind that the units here are a bit awkward. I'm just generalizing here in terms of units. Suppose that N, okay, is the sum of all the reaction order, okay? And this we can call the overall reaction order. It's the sum of all the exponents. You can hear me, right? Still.
Sí.
Okay. Then you can derive the units, because whatever goes to the power of N, okay, is a molar concentration. So it's mole per centimeter cubed to the power of N, okay? Well, this we know to be a molar concentration per unit time, okay? It's the rate of change of molar concentration. So in fact, K ends up having very, very strange kind of units, because in order to when multiplied by this to get this, you have a mole per centimeter cubed to the power of 1 minus N, okay? And then times 1 over S. So this is the units 1 over seconds. It's the units of this reaction rate, okay? However, if the overall reaction order is really 1, okay, K has these nice units of 1 over time. So in fact, this reaction constant, if the reaction order, overall reaction order is 1, ends up having the units of the inverse of a chemical time scale. Okay, that's also very important. Okay, you could see this over here. You can see that K is really has the units of 1 over S, so that this is dimensionless. Okay, and in fact, the reaction order here was 1. Okay. Okay, we have 5 minutes. Now, these reaction orders, generally speaking, so the individual reaction orders, generally speaking, alpha and beta, are not equal, as you can see, to the stoichiometric coefficients A and B. Although in this particular case, they were, look, 2 and 1, right? So they're generally, as I said here, experimental results. Okay. Now the reason for this lies in the fact that, generally speaking, I have considered here a global reaction. So this is really not what's happening at the molecular level. Okay. We're used to thinking of reactions as single collisions between, at best, 2 molecules, right? You can have one dissociation when one molecule breaks up. You can have at best a bimolecular reaction. You can have a trimolecular reaction only in particular cases, okay, where you have, let's say, 3 molecules. Think of collision like an accident between 2 cars. The chances of having an accident between 2 cars is very high, right? But the probability of having an accident of 3 cars hitting at the same time, because that's what should happen, it's a little less probable. In fact, it's hugely improbable. So this global process here, generally speaking, is not a collision, but it's really the sum of many what we call elementary reactions, okay, which are indeed themselves collisions between molecules, okay? So this is a macroscopic representation, this reaction here, this global process here, of the sum of what we call elementary reactions. What is an elementary reaction? An elementary reaction, let me write it here. Okay, is an actual collision process between molecules or atoms. Okay, so when I write it down, okay, I write down a chemical reaction, this actually represents what's really going on at the molecular level. Okay. Now the number of so do you want me to write it down? No, well, you wrote it. So an elementary reaction is an actual collision process. Okay, we talk about molecularity if the reaction is, for example, unimolecular or bimolecular. Okay, so being a representation of the actual collision between molecules. Okay, it can be unimolecular if it's like a dissociation, so you have just one molecule breaking up, or very often it's bimolecular. Okay, so you have the collision of two molecules. Okay, now I will leave you with the let's say conclusion of this discussion, that having introduced elementary reactions, okay, for these elementary reactions, okay, we find that the reaction orders, alpha and beta, are always equal to the stoichiometric coefficients, okay? So that explains, okay, I'm going to go over this next time. That explains why, for example, in this particular case, the reaction orders are exactly equal to this, okay? And in this particular case, on the other hand, here, you see, it was not, okay? So sometimes you have an elementary reaction, okay? And for those reactions, you can definitely derive the reaction rate directly from the stoichiometry because the reaction orders are equal to the stoichiometry. And in other cases, it means that it's a global reaction, so the reaction orders are really something else because they are derived experimentally. But I'll get back to this next time. I'll be a little bit more precise, okay? For the time being, I guess we can end it here. And I wish you a good weekend.